Good morning, everyone. Good afternoon, good evening, depending on when you are seeing this. My name is Kunle Okikiola, popularly called Olakunle, your chemistry online tutor. So here we have our wire question today. So the question says, calculate the volume occupied by 2.5 moles of an ideal gas at minus 23 degrees Celsius and 4.0 atmospheres. We are given our gas constant R to be 0.082 atm dnq per Kelvin per mole. The first thing is to identify the topic and what you are solving. This is actually gas law, which of them the ideal gas. Underline this, I'm coming back there. Now let's start. Calculate the volume. We have the volume, we don't know. We are looking for occupied by 2.5 moles. The mole equals to 2.5 mole. All right, of an ideal gas at minus 23 degrees Celsius. Our temperature equals to minus 23 degrees Celsius. Now we have to convert this degrees Celsius to Kelvin straight up by adding 273. So when we add 273 to our given value of temperature in degrees Celsius, we have it to be in Kelvin. So minus 23 degrees Celsius plus 273, we have 250 Kelvin. We converted this degrees Celsius to Kelvin now. We are done with that. And 4.0 atmospheres. What was measured in atmospheres? That's what? That's pressure. So our pressure equals to 4.0 atmospheres. That's ATM. Alright now. So we have our gas constant R to be equals to 0.082 atm dm³ per Kelvin per mole. We have this. So before we start solving, I want to draft out the formula. Majorly, this is the formula. PV equals to RNT. This is the formula we use under ideal gas. But I want to draft it out. This formula here is actually gotten from, we have gas laws. We have about 9 of them. So we have Charles' law. We have Boyle's law. And we have Avogadro's either law or you call it principle. Alright, now let's take Charles' law. Charles' law states that the volume of a fixed mass of gas, that's the volume of a fixed mass of gas, is directly proportional to its absolute temperature in Kelvin. Note that. So we have this. Coming to Boyle's law now, Boyle's law states that the volume of a given mass of gas inversely proportional to its pressure at constant temperature, here at constant pressure. Then Avogadro's law of principle states that equal number of volume contains same number of mole. That is, volume varies directly as number of mole. Now let's combine these three together. We have volume, volume, volume. Let's combine. So you can say volume varies directly as T, also as N here. So volume varies directly as T and N, and inversely directly or proportional to what? To the pressure. From here we are going to have what we call, we have V equals, now this thing will turn to equals to K, that's in mathematics, equals to KTN over P. But here in chemistry or under this topic, we don't use this K, we use R instead of K. Instead of K now we use what? We use R. Then from here, let me know here. So from here, I will have V equals to RTN over P. And R is the what? Universal gas constant. It has different values depending on the unit. This or the unit of which pressure is measured. Because we have different units in which pressure is measured. We have in ATM, atmospheric pressure. We have in millimeter of mercury, we have in bar, we have in torr, we have in Pascal also, depending. Now the one we are given is ATM. So let me get this, let me derive the value here. You know, from here we have V equals RTN over P. I want to make this R a subject formula, so let's cross multiply. From here we have PV equals to RTN. The formula that was here, but that's not what I'm going to. I want to derive this R out. Divide it by Tn by Tn. So R equals to PV over Tn. Now, for pressure, we are given in 1 atm, and that's standard pressure. In millimeter mercury, that's 760. But here in ATM is 1. Then our volume, the standard volume is 22.4 dm³. We call it GMV, gaseous molar volume. Standard temperature is 273 Kelvin. And number of mole is what? 1 mole. As 1 mole is still equals to everything here. From here now, let's input all this. Let's substitute them into the equation here. So we have R equals to our pressure 1 atm times our volume 22.4 dm³ over our temperature. This is here 273 Kelvin times then our number of mole. We have what? 1 mole. Multiply our R equals to 1 times this. We have 22.4 atm and we have dm³ over this times this. We have 273 Kelvin and what? Kelvin mole. From here, let's divide. So you have our R equals to 22.4. Sorry. We divide it by 273. That equals 0.082051. But if I should approximate now, I'm going to have my R equals to 0.082. This 521 then here. So that's nothing. So I have ATM here. I have dm³ per Kelvin and I have per mole. So here, this is what we have here. This is what they give us. So this is here. Now we can solve now. From here, we have this is what we are looking for. Volume. Volume equals to we have RT or RNT over P. We are looking for volume here. So our volume equals to what was our R here? 0.082 times our temperature, which is 250 Kelvin. Because of space, I can't put the unit. Then times the number of mole from the question. We have 2.5 mole. And the pressure given is what? 4. So our volume now equals 0.082 multiplied by 250, then multiplied by 2.5, and that equals 51.25. We divide it by 4. So the volume equals 12.8125. Let me approximate. My volume now will be equal to 12.80 dm. Because majorly in chemistry, our answer should always be in 2 decimal places. Even when we have 4, we should write it as 4.00. All right now. So the volume here is what? 12.80 dm³. Now let me come back to this. Ideal. This is our correct answer. Now ideal. What does it mean of ideal? Ideal means something to be perfect. Ideal means perfect. Now we are calling this ideal gas. So the question is, can a gas be perfect? Can a gas be ideal? Let me hear from you in the comment section. God bless you.